All right. Today we got an order of business to get to first. We are effectively one lecture ahead. So the exam, your first exam was going to be on next Wednesday. It's still going to be on next Wednesday. I'm not going to move it up because we're ahead. I just want to make you guys aware of that. There will be an in-class exam next Wednesday, and then an associated take-home portion of the exam that will be due I don't know, at some later time. It's on the syllabus when the take-home portions are due. I think I'll give you guys a couple of days. The material that will be covered on the exam will be all of the op-amp stuff and then everything up to what we talk about today, which is second order circuits, which contain multiple of the same energy storage elements. C circuits that contain two inductors or two capacitors that can't be combined. And the example problem I've chosen for today is much less terrifying than the one we did the other day. So your homework problems are significantly easier as well. I'm not saying we're not going to get bogged down in some calculus. I am saying it's not going to take 3 pages of calculus to get to a result. So, all right, with that in mind, let's go ahead and jump right in. Our circuit of interest is as follows. We have 7-volt source. Let's call this guy R1. Sorry, actually, I'm putting numerical values here so we can actually calculate things. 3 ohms, 0.5 henries. One ohm. And let's see, 0.2 henries. Let's call this guy 5 ohms. And our ultimate goal in this is to figure out what this voltage drop over the 1 ohm resistor is. Okay. So hopefully it's fairly apparent that this is going to be a general RLC circuit because once that switch changes from, let's call it down here, position A to position B, we have a resistor in series with an inductor, and that is in series with a parallel combination of a resistor and another inductor. So it's definitely not a simple series RLC circuit or series RL circuit. It's definitely not any type of circuit containing a C at all, actually. It's not parallel either. All right, so during the transient condition, meaning T greater than or equal to 0 plus, our circuit is going to look like this. I'm going to solve things symbolically again because it's going to be, in my opinion, significantly less confusing. So let's call this guy R2. Let's call this guy L2, where I just want to be clear that R1 is 3 ohms, R2 is 1 ohms, L1 is 0.5 henries, L2 is 0.2 henries, and finally Vs is 7 volts. Now, ultimate goal is to figure out what VR is. At this point, we are not concerned with that. We are simply trying to develop the second order differential equation, either in terms of IL1, which I'll define momentarily, or IL2, also, which will be defined momentarily, so that we can get an assessment of whether the circuit is overdamped, critically damped, or underdamped. So with that in mind, I'm going to define my variables. This is going to be VL1 as a function of time. This will be VL2 as a function of time. This current is IL2 as a function of time. And this current is IL1 as a function of time. Now, how I am going to approach this is let's give effectively what's mesh analysis a whirl. So I'm going to call this current IA as a function of time. Notice that it's the exact same thing as IL1. And I'm going to call this current IB as a function of time. And it is the exact same thing as IL2. All right, just for explanation purposes. So if I apply Kirchhoff's current law at mesh A, what am I going to get? Somebody tell me what's happening here. Use the symbolic stuff, please, sir. Negative Vs, okay.
Plus IA
All right. So it's going to be the voltage drop over inductor 1, right?
Yeah.
So how do we express the voltage? Okay. L1 DIA by dt. All right, what's next? All right, is equal to 0. Okay. Everybody okay with that? Anybody see anything weird? All right, so I can notice pretty easily that the quantity IB only shows up in one term. So I'm going to go ahead and I'm going to isolate that guy, meaning I'm going to move R2 times IB to the right-hand side. And I'm going to divide everything by R2 as well, so that I get IB by itself. So what this should give me, IB of T is going to be equal to L1 divided by R2 times the derivative of IA with respect to time plus 1 plus R1 over R2 IA minus Vs over R2. Well, let's double check here just to make sure I haven't made any wonky algebraic mistakes. So what I've done is I've combined this R1 times IA plus this R2 times IA, giving me R1 plus R2 quantity times IA. When I divide it by R2 to get IB by itself, I have R1 plus R2 divided by R2, which gives me 1 plus R1 over R2. So that's where that guy came from. Just want to be very, very clear about that. So here's one equation. Pretty reasonably easily come by. Since we have IB by itself expressed purely in terms of IA, I'm going to go ahead and take the derivative of this guy with respect to time, so I'll get a relationship for the second derivative of IB expressed purely in terms of IA. So second derivative means I take the, or if I take the derivative of this guy, I'm going to have dIB by dt is going to give me L1 over R2 times the second derivative of IA with respect to time squared plus 1 plus R1 over R2 times the first derivative. And then the derivative of the constant term at the end obviously goes to 0. So I have an equation for IB in terms of IA, and I have an equation for the derivative of IB also purely in terms of IA. So really I just need one more equation that's going to somehow relate IA and IB so that I can make a substitution and get my total differential equation here. And so what I'm going to do is I'm now going to apply Kirchhoff's current law around mesh B. So this should give me R2 times IB minus IA plus the voltage drop over inductor L2, which is simply L2 times the derivative of IB with respect to time is equal to 0. Easy enough, right? Since I know what IB is with respect to time purely in terms of IA, and I know what the derivative of IB is with respect to time purely in terms of IA, I can simply substitute equation 1 and 2 into equation 3. And what I will get is, so let's see, I'm going to have negative R2 times IA of t. That's just me multiplying R2 times negative IA in that first bit, plus R2 multiplied by equation 1, right? Because I'm simply substituting in here IB of t. So it's going to be L1 over R2, the derivative of IA with respect to time, plus 1 plus R1 over R2 IA with respect to time, minus VS divided by R2, plus L2, and now I'm going to substitute in equation 2 directly. L1 over R2, second derivative, plus 1 plus R1 over R2, first derivative. And this whole thing is equal to 0. From this point, it's simply joining like terms and all that kind of stuff, right? So, for instance, my second derivative term, I have L1 multiplied by L2 divided by R2. times the second derivative of IA with respect to time. So that takes care of this guy right here. For my first derivative term, I have, make sure things are looking straight here. L1 plus L2 times 1 plus R1 over R2, the first derivative with respect to time. So to be clear, that's me taking this guy right here, where R2 times L1 over R2 just gives me the L1. And also this guy right here, where L2 times 1 plus R1 over R2 is where that shows up. So algebra seems okay right there. All right, then let's see what else I am going to have. So I have negative R2 IA. So let's do it like this. I'm going to have R2 times 1 plus R1 over R2 minus R2. So that's this guy and this guy, IA, will be equal to DS. And we can actually simplify the term on IA a little bit here, I believe, because R2 times 1 plus R1 over R2 is simply R2 plus R1, right? R2 plus R1 minus R2, that whole thing is just R1. So I'm going to scratch that and just put an R1 here. And what that leaves me with is alpha is going to be L1 plus L2, 1 plus R1 over R2 divided by twice R2 over L1 times L2, right? When I no, L1, L2 over R2. And omega naught is going to be square root of R1 divided by L1, L2 over R2. Divide by that fraction. Yeah. Okay. So let's put in some numbers here. I need to find my calculator. So if L1 is 1/2 of a Henry, we have 0.5 plus 0.2 multiplied by 1 plus R1 was 3 ohms. Over R2, which was 1 ohm. That whole thing is over twice. L1 0.5 times L2 0.3 divided by R2, which was 1 ohm. 4.3333. Let's multiply that by 3. 13 thirds. Nepers per second. Omega naught. Figure that guy out. So we have R1, which is 3 ohms, divided by 0.5 times 0.2. This guy is going to be the square root of 30 radians per second. And just because I don't know what the square root of 30 is off the top of my head, although I feel like it's 5.477 radians per second. All right, so from this is our circuit critically damped, overdamped, or underdamped. 13/3, again, 4.333. Underdamped, right? Because omega naught is greater than alpha. All right, and then from here, we can simply proceed as if it were any other regular old circuit. But while we're at it, let's calculate omega D. So that is going to be square root of 30 minus 13/3 squared, 3.35. All right, so analyze the circuit at t is equal to 0 minus. So let's look up here. All right. So the things that we're going to be having to pay attention to are IL1, BL1, IL2, and BL2 again. Can we all easily agree that all 4 of those quantities should be 0 when there's no source connected to the circuit for a very long time? So we don't need to do any analysis whatsoever. All right. IL1, 0 minus, 0 amps. IL2, 0 minus, 0 amps. BL1, 0 minus, 0 amps. BL2 at 0 minus equals 0 amps. All right. Now we analyze. Yes, you're right, volts. Thank you. At t is equal to 0 plus. Here's our 7-volt source. Here's our 3 ohm resistor. We're going to have an open circuit here. Here is our 1 ohm resistor. IL0 plus, IL1, excuse me. IL2 at 0 plus. All right, so we know IL1 at 0 plus has to be 0 amps. IL2 at 0 plus has to also be 0 amps because the current cannot have changed abruptly. what's going on with these voltages. Anybody have any thoughts? Pardon? Okay, but which one specifically are you referring? Okay, so the argument is that the voltage drop over inductor 1 is 7 volts. I agree with that, okay? So it should be fairly obvious that the current flowing through the 1 ohm resistor is 0 amps because it's not connected to a closed circuit, so current can't pass through it. We all in accord there. So if there's no current flowing through the 1 ohm resistor, then that means that there's no voltage drop over the 1 ohm resistor, which means VL2 by definition has to be 0 volts. And because there's no voltage drop, when we perform Kirchhoff's voltage law around that loop, that means that VL1 has to be, go away, calendar thingy, 7 volts. Circuit analysis seem reasonable to everybody. All right. Now let's look at what's going on at t is equal to infinity. So at t is equal to infinity, we have our 7 volt source. Here's our 3 ohm resistor. This is our current source, excuse me, not our current source, our inductor, IL1 at infinity, VL1 at infinity. Here is our 1 ohm resistor. Here is IL2 at infinity. Here is VL2 infinity. So let's see what's going on here. IL1 at infinity is equal to something. IL2 at infinity is equal to something. And VL1 at infinity has to be 0 volts. VL2 at infinity must also be 0 volts because they represent the voltage drop over short circuit. So those guys are pretty simple. So what is IL1 and IL2? What are they going to be? 7 over 3. Ohm's law. V is equal to IR, I is equal to V over R, right? And they're going to be the exact same thing because all of the current flowing through IL2, because it's a short circuit, will bypass that 1 ohm resistor. So 7/3 of an amp and 7/3 of an amp. Everybody in accord there. All right. So we got all 3 of our conditions at t is equal to 0 minus, t is equal to 0 plus, and t is equal to infinity. We know that the circuit is a underdamped circuit. So now we're ready to rock and roll with setting up our system and all that jazz. So I guess before we do that explicitly though, what quantity should we solve for, right? Meaning, should we solve for the inductor current in L1 or the inductor current in L2 and use that to get to our quantity of interest? Our ultimate goal being to get the voltage drop over that 1 ohm resistor. So if we find the current and voltage through inductor L2, then we're good to go because the voltage drop over inductor L2 is the same thing as the voltage drop over the 1 ohm resistor, which is what we are trying to find, right? So finding really anything about inductor 1 is a waste of time. All right, so with that in mind, we know that IL2 as a function of time will be of the form B1 cosine omega dt plus B2 sine omega d, sorry, there should be a t there, t e to the minus alpha t plus IL2 at infinity, because this is a total response problem because our value settled to something that is non-zero. IL2 at t is equal to 0 plus reduces to B1 plus IL2 at infinity. If we put in our numbers, IL2 at 0 plus was 0 amps is equal to B1 plus 7/3 of an amp, which gives us B1 is equal to negative 7/3 of an amp, if my algebra here is correct. And I remembered the values correctly. So everything seems okay thus far, right? All right, I don't have my sheet in front of me, so forgive me if I make an error here, and by all means, correct me. Omega d b1 plus alpha b2 sine omega dt e to the minus alpha t. Did I get that right, or did I switch where b1 and b2 were supposed to go? You guys have the sheet thingy, I don't. So I'm trying to do this from memory from months ago. Looks good? All right. Okay, so from this, VL2 at 0 plus becomes L multiplied by omega d B2 minus alpha B1. So that means VL2 at 0 plus, that was 0, right? Yeah. So because it's 0, I'm going to divide both sides by L and not worry about it, which actually means omega d B2 is equal to positive alpha B1. And we know what B1 is, so from that, B2 is alpha over omega d B1, where alpha was 13/3, omega d was 3.35. And then here we have B1, which is negative 7/3 of an amp. Get negative 3.018 amps. So from this, VL of t is going to be omega D 3.35 per second times B2 negative 3.018 amps. Sorry, should be an L in here as well. That's what I'm missing. Sorry about that. L2. All right, so omega D 3.35 per second, negative 3.018 amps, cosine 3.35 T. No, that's B1, sorry. Confusing myself. Negative 7/3. Oh my goodness, I'm blowing my own mind here. I'm screwing this up so bad. All right, omega D times B2. So I was right. I'm just losing my mind. I apologize. Negative 3.018 amps minus alpha, which was 13/3 times B1, which was negative 7/3. Cosine 3.35 T minus omega D 3.35 per second times B1 negative 7/3 of an amp plus alpha 13/3 times B2 negative 3.018 amp sine 3.35 T e to the minus 13/3 T. And now, finally, let's throw some numbers in, or do some calculations here. So 0.2 times 3.35 times negative 3.018. Store this as y. All right. 0.2 times x times y minus 13/3 times negative 7/3 . So this guy right here, I get goes to 0. Anybody confirm that? Their calculator or whatever. Then I have 4.179 sine 3.35 T e to the minus 13/3 T. That's what I got. Anybody with a calculator try to do this, or said screw it? All right, well, the methodology is correct even if the numbers aren't, but I feel like the numbers are correct here. All right, so I don't really have anything else prepared for today. I mean, we could work another general RLC circuit problem if you want to see me do a bunch of substitutions and stuff. If not, I'm free with letting us get out early. Your choice. I'm happy to work more example problems. I'm also happy to look over some of the homework problems and use the remaining time to answer any questions you may have. You just raised your hand.